All right, hi you guys. So today I'm doing something a little bit different. Instead of a regular lesson that's based on a note section, I'm going to go over a few questions that a student had from the self-test as well as the chapter review. And the reason why I'm posting this online is because I'm hoping that for some of you, if you have struggled with similar questions, then this will help you, because you really should be going through these self-tests and chapter reviews at the end of each section in order to determine whether or not you're ready to proceed to the test. So basically you should be going through these tests as well as the reviews, trying all the questions, and then comparing your answers to the answers in the solution manual that's posted online. And then if you're not getting the right answers, you need to figure out where you're making the mistakes. And if you can't figure that out, then you need to contact me and ask me for help with it. So I can either help you one-on-one, or you can just send me the number and the page of the question, and I will send you a video like this. So this was in response to one student's questions. So these might not be all the questions that you would have had, which is why you can then contact me, but hopefully this will help you out. So you can watch through them, see if any of the questions match up with ones that you had, and yeah, and then hopefully that'll help you get on track for studying for the chapter test. So the ones that I'm going to be covering today, just so you can see right away if this is going to be worth your time, like if you've struggled with any of these. So on the self-test for chapter 8, question number 4, I'm going to be covering B and C, and I'm also going to cover number 5. And then for the chapter review, so page over, I'm going to be looking at, let's see, 4, 7, and 8. So 4 is this one with the room. Sorry, it's kind of hard for me to move the textbook over further. 7, 8, and then 11, 13, 14, and 15. So 11, 13 with the plane, 14, and 15. Those are going to be the ones that I'll cover. So if you've had any struggles with those, then watch this and it will help you to understand how to solve these types of problems. All right, so the first one we're looking at is this self-test one. So it says, to save money, a company makes drinking cups for dentists that and they've decided to reduce the size of the cups by a scale factor of 3/4. Okay, so the first part here asks for the radius and height of the new cup. Okay, so I said I wasn't going to do A, but actually the second part here asks for the slant height of the new cup, and in order to solve for that, we're going to need A to solve for A as well. Okay, so basically we have, let's see, we have this cone here, and it is 6.3 going across, and it is 9.1 from top to bottom. Okay, so my classic good drawings. All right, so this was our original, and we are reduced by a scale factor of 3/4. So, and then what we're going to be looking for in part B is the slant height. So some of what might be tricky with this question is the terminology. So slant height is always the diagonal distance, essentially, on any kind of three-dimensional shape. So it's going to be S is going to be the length of this side. Okay, so what we can see here is that in order to solve for the slant height, we can basically think of our cone as being like a right triangle. So we have the height here, 9.1 centimeters, and we have a distance from there to here, which is half of 6.3, right? That was our diameter. So if we start right from the middle height and we go over to the edge of the cone, it's going to be half of 6.3. And then we can solve for slant height using Pythagoras, right? Because it's going to be the two sides to solve for the hypotenuse, basically. All right, so in order to do that, we need to know what the values are for these numbers here. So first of all, 9.1 is one of our values. And so this is what you would be doing in part A, and you want to solve for it by multiplying it by the scale factor. Now the scale factor is 3/4. So with that kind of a nice easy number, basically what I would do is 3 divided by 4 gives me 0.75. So I'm just going to multiply by my scale factor. So 9.1 times by 0.75 gives me 6.825 as my height. Okay, and then for radius, remember radius is going to be half of this value, so let's start out by doing that. So 6.3 divided by 2 gives us 3.15 centimeters, and then we need to multiply that by the scale factor, so times by 0.75 times by 0.75, which is going to give us 5.11875. Wait a minute, that doesn't make sense. Oh, because I'm putting that in. And that's why it's always good to check your answers. So sorry, it was the 3.15 that I wanted to multiply by 0.75. There we go. That makes more sense. Oh, and I'm out of whiteout. Okay, so I'll just do this. 2.3625. That makes a lot more sense for being 3/4 of 3.15. Okay, so that's our radius. So now to solve for our slant height, basically we just need to think about this as being like a squared plus b squared equals c squared. So we can say slant height is equal to our height squared, so 6.825 squared, plus our radius squared, 2.36 squared, and of course we'll need to square root it. And that is going to give us 7.2 centimeters. Okay, so there is our slant height. Now, what's the next thing that we're asked for? The next thing it asks is how much material does the company save for each cup it makes? Okay, so this was for B. And then for C, how much material does the company save? So when we're thinking about how much material we're using to build something, it's always going to be a matter of surface area, right? So how much material would you need to make these cones? So with surface area of a cone, we have the formula on our data sheet here. And the main thing we need to think about with this situation is that when you have a drinking cup at the dentist, you know that even though it's shaped like a cone, the bottom doesn't have anything on it, right? The way we would normally think of a cone as having like a circular surface on the bottom. So because the only material is going to be the stuff that goes around the sides, we need to analyze our formula for surface area of a cone and consider what parts we actually need to use. So pi times radius times s. S is our slant height, which is right here. And so that part of the formula is finding the surface area of the part that goes around. Pi r squared is the radius, or is the, surface area of a circle, which would be the base of the cone. And because we don't have a base, we don't want to include this in our calculations. So we're going to just do surface area is equal to pi rs. Pi rs. And so for our new cone, we know that radius was 2.36. 2.3625 centimeters. And we have to multiply that by the slant height, which we just solved for. Now, when I gave my answer, I rounded it off, but make sure that in your, like, if you move on to use that number for further calculations, that you use the unrounded value. So I think it was 7.2 repeating is what I got, centimeters. So now for my surface area, I'm going to do pi times 2.3 times by 7.2, and that is going to give me 53.60 centimeters squared, so rounding it off. Now, in order to know how much material the company is saving, I need to know what the previous surface area was and find the difference between them, because that's the amount that's being saved, right? So previous SA is going to be pi times by. The original radius was the 3.15 times by let's see, original slant height, which we never calculated. So we're going to have to really quickly figure that out. So the original slant height would have been 9.1 squared plus, so a squared plus b squared. So remember to use the radius here, 3.15 squared, and then square root that. And that will give us 9.629, some kind of a long decimal there, so we'll leave it off as that. And our units are centimeters. Okay, so now we can plug that in here, 9.629 cm. And what we end up with there is 95.296, again a longer decimal, centimeters squared. Remember that your units for surface area are always going to be squared, because when we do our math, we're multiplying the units by each other. Okay. And so now to finally answer the question, we have the two different surface areas. So the difference is going to be the original 95.296 minus 53.60. Again, use your full decimal if you got a full decimal there. I can't remember exactly what I calculated there. And you should end up with 41.69. 41.69 centimeters squared is how much they save. Okay, so if this was a written question on a test, you would just want to write down they save 41.69 centimeters squared per cup. All right, and yeah, so then the next question for D, just to quickly let you know, it asks you when filled, how much less water does the new cup hold? So again, you would just go ahead and use, you have volume of a cone here, so pi times radius squared times height. So it's a little bit easier of a formula because you don't have to worry about the slant height. So basically you would just solve this for the previous dimensions, and then for the modified radius and height dimensions that we came up with up here at the top, the 6.825 and the 2.3, and then just find the difference the way we did for the surface area. Okay. All right, let's try question number 5. So with question number 5, we have a cord of wood is stacked in a pile with a volume of 128 feet cubed. 3 cords of wood will be stacked in a pile with dimensions that are similar to the dimensions of the first cord. Predict how much longer the second pile will be compared with the original. Okay, so we're given the dimensions in here, so you can always follow along in your textbook. It's kind of hard for me to get both the textbook and my work in the shot here, so you can follow along in your textbook. It's on page 504, by the way, if you haven't found it. So let's see, we're told that we have a volume of 128. Volume equals 128 feet cubed. So again, remember with units, when you're dealing with volume, the units are always going to be cubed because you multiply the units together 3 times. So this is the original volume, and we want to have 3 cords of wood will be stacked in a pile with dimensions that are similar to the dimensions of the first cord. Predict how much longer the second pile will be. So basically we're going to have, if a cord is 128 feet cubed, we're going to have 3 times that. So the new volume is going to be 128 times by 3. Okay, so it's going to be 128 times by 3, which would be 384 feet cubed. Okay, and In the original one, so what we also want to think about is the chord is making up kind of like a rectangular prism. So I'll show you the picture again, right? So it's going up, back, and across. So there's the 3 dimensions that we think of with a rectangular prism. And when we're solving for volume, it's on your sheet, but you probably already know this for a rectangular prism. It's the area of the base times the height, which basically means it's width times length times by the height, right? Because this is the area of the base is 4 times 8. So we can say that this volume, the original one of one chord, which was 128 feet cubed, is equal to 4 times 4 times 8, because those are the dimensions of the pile. Okay, so let's say width times height times length. Now we have this new volume that's 384 feet cubed, so it is going to be equal to some set of dimensions being multiplied by each other that we need to solve for. Now it said in the question that they want the dimensions to be similar, so basically what that means is that they need to increase, all of the dimensions should increase by the same scale factor. So essentially what that means is we're going to have 384 feet as our volume is going to be equal to a width times a height. If we look at the relationship between these dimensions, we see that it's a 1-to-1 ratio here, right? 4 to 4. And then the length is double these two. So if we want to set that up in terms of like algebraic terms, we could say, let's just say the width and height are both x, because they should be the same, the width and the height. And then the length has to be double those values, so it's going to be times by 2x. Okay, so now we have a kind of like a formula that represents how we would solve for the volume of the new pile. And we can simplify this by combining like terms. So we can say 384 feet cubed is equal to, so remember when you're multiplying an algebraic term like x, then you are basically just adding exponents for how many times you multiply. So if we have x times x is going to be x squared because we've multiplied it by twice, and then we have another x is going to be x cubed, and then the 2 out front just stays the same. So we end up with 2x cubed. Okay. So now we can start looking at solving for what would x be, right? Because we only have one variable. So the first thing we want to do is remove the 2. So divide 2 out of both sides. Now we're left with 384 divided by 2, which is 192, is equal to x cubed. Now if we want to get rid of the cubed, we need to cube root. And if we do that to one side, we need to do it to the other. So we're going to be left with x being equal to the cube root of 192, which is 5.76 feet. And again, that's like a bit of a longer decimal. Okay, so don't round it yet though, because we still need to use it for some of the math. So they are asking how much longer the second pile will be compared with the original pile. So when we did this formula here, remember it was width, height, and length. Okay, so length is actually 2x. So if we want to know the new length of the pile, x tells us the width and the height, but the length is twice that value. So length equals 2 times by this 5.76 decimal number, and that gives us 11.537 feet. They're asking how much longer is this than the original, so we just need to find the difference between those again, just like we did in the previous question. So it's going to be 11.537 something minus 8 feet, which is going to give us 3. Let's round it off to 3.5 feet longer. Okay, so the new length of the pile is 11.5 feet, but it's 3.5 feet longer than the original pile was. Okay, so those are the only questions that I had for the Chapter 8 self-test. So now let's move on to the chapter review. So you're going to have to flip over a couple of pages to 507. And, sorry guys, I got to move some stuff around here so I can get this page in. Okay, so the question from this one is, Doris wants to buy new carpet for her living room, which has the dimensions shown. She plans to order about 10% extra so that she has enough to allow for loss during cutting. She can buy her carpet locally for $36.95 per square yard, or in a store in a nearby city for $33.99 per square yard, but then there's a delivery charge. So we have two questions here. How much carpet should Doris buy? And where should she buy the carpet? So presumably based on the prices, we want to try and figure that out. Okay, so how much carpet should Doris buy? Well, in order to start looking at this, we need to figure out what the dimensions are, kind of in a more usable form. So basically, the dimensions that are given in your textbook here are in inches and feet. So just always remember, if there's one apostrophe, it means feet, and two apostrophes means inches. And because the prices are in yards, we want to determine how much she needs in yards as well. Let's see, and I think it even said she can buy... Oh, it doesn't say that earlier, but yeah, if you're going to have a price at a certain dimension, then you want to solve for that dimension. So we want to break down this drawing here. So I'm going to make kind of like a rough copy of it here. Okay, and so what we're told at the beginning is that we have 12 feet up here. And if you look on your table here, so depending on which ones you're doing, so this one is nice and easy because it's just 12 feet even. So we can use our conversion factor here for going from feet to yards directly. For some of them, like on this side, you're told that it's 14 feet and 6 inches. So in this case, what I would probably do is convert the whole measurement into inches and then convert that back into like feet and yards. So I'll show you how to do that in a minute. But for this one, it's nice because we just have 12 feet and there's 3 feet in every yard. So basically, there's different ways you can kind of think about this. You can kind of logically think, like, if I have 12 feet and there's 3 feet in every yard, 12 divided by 3 is 4. So then that means I have 4 yards, right? The other way you can think of it is to use a conversion factor, and that's usually what I do because we use it a lot in the sciences, which is kind of more what I'm used to teaching. So we have 12 feet here. If we want to figure out how many yards, then basically we want to multiply the measurement we're given by a fraction that contains what we want, which is yards, and what we need, what we already have, which is feet. You always want to put the thing you already have on the bottom of the fraction because basically the math means that you will divide that value away and cancel it out. So essentially I'm going to go 12 feet times by the units I want are always on the top, so 1 yard, and then divided by 3 feet on the bottom. So 12 times by 1 is 12, divided by 3 is 4 yards. And then my feet end up canceling out. Okay, so now I know this length is 4 yards. On this side, I want to, because I have inches added in, I want to convert the whole thing into all inches. I don't ever want to have mixed units like this. So remember when you see 14.6, it's not 14.6 because imperial measurements don't work on like a base 10 system the way we do. So it's not a decimal 6, right? Because there's 12 inches in a foot. So 14 feet and 6 inches is not 14.6 feet. So what I need to do then is say, okay, there's 14 feet total. And there's 12 inches in a foot. So times by 12 inches per foot gives me 14 times 12. Sorry guys, I gotta grab my calculator. 14 times by 12 gives me 168 inches. Now I had 14 feet, which I just accounted for, but I had 6 extra inches, so I need to add 6 inches. And 168 plus 6 is going to give me 174 inches. Okay, so now if I want to solve for this side in yards, I need to say, okay, I have 174 inches. I'm going to show you guys the conversion factor when we multiply it all together, and then maybe how the units cancel out will make more sense to you. So 174 inches is what we have. We want to multiply it by, let's convert it first into feet, which might sound weird because we had it in feet, but what we're going to convert it into now is feet where we have the whole thing in feet. So it'll be like 14 point something feet. So 174 inches times by, if we want to convert it into feet, the units we want, remember, always go on the top. So there's 1 foot in the units we already had can go on the bottom, 12 inches. So now you can see how, because whenever we multiply something by a fraction, we're multiplying it by the numerator on top. So inches become divided by inches, so they cancel out and we're left with feet in our units. 174 divided by 12 gives us 14.5. Okay, now depending on how comfortable you are with imperial measurements, you might have known, like, because there's 12 inches in a foot, you might have known right away that this was 14.5. So if you know that, that's great, you can go ahead. But if you ever need to use the conversion factor, then that works out as well. So we have 14.5 feet and we want it in yards. So we're going to do the same thing, multiply it by a conversion factor where we already have feet. So we want that to go on the bottom, so 3 feet. And we want to know how long that is in yards, so 1 yard goes on top. And so now we find that that length is 4.83 repeating yards. Okay, let's see, what other lengths did we have? So on the bottom we had 20.8 or 20 feet and 8 inches. And 8 inches. Okay, so again, I'm going to have to do 20 times by 12 equals 20 times by 12 gives me 240 inches plus the extra 8 inches, which gives me 248 inches. Oops, 248 inches. So now I just need to say, okay, 248 inches. And what I can actually do if I want now is combine these two conversion factors. So I'm going to do it multiplied by, I can already see what I had to do here, multiplied by 1 over 12. And then I had to take that number and multiply it by 1 over 3. So I can just do those in a row to speed things up once I've figured out carefully what my conversion factors are. So 248 times by 1 over 12 times by 1 over 3 gives me 6.8 yards. It's still a good idea to double check and make sure that you know that it kind of makes sense. So if there's about 3 feet in a yard, and we have 20 feet, let's say, you want to kind of figure out if that would work out. So basically 20 divided by 3, well, 3 goes into 18 6 times, so it makes sense that we're a little bit over 6 here. Okay. Okay, last two sides here. On this side it was 6 feet. So 6 feet times by, so again, because we just had 6 feet even, we can use the direct comparison. So there's 3 feet in every yard. So 3 feet units we have on the bottom, units we want on the top. So 6 divided by 3 gives us 2 yards. And then this last one here is going to be a value that we actually don't know. So what we would want to do, because they don't give us this measurement, so we need to solve for this value. How can we do that? Well, we can look at kind of what we have originally. So on this side here, we said that it was going to be, I'll maybe just box these in so we know which measurements we're using, so that we don't have to do more conversions than we need to. We're going to use the yard measurements instead of the feet to get this side. So if this long side here was 4.83 yards, this side is this length minus that initial one. So it's going to be 4.83 repeating yards minus 2 yards is going to give us 2.83 repeating yards. Okay. Perfect. So now we have all of our dimensions. So let's go ahead and start solving. So she wants to basically figure out the area of carpet that she needs. So when we have shapes like this, where it's not just one set shape that we know, like a square, for example, then we call it a composite object. And basically what we want to do is break it down into two shapes that we can easily solve for. So you can break it up two ways. You could either draw a line here and solve for this rectangle and that rectangle, or you could have drawn a line here and solved for this rectangle and this rectangle. So I'm going to do this way. Either way would be right though. So for the first rectangle, let's call this number 1 and this number 2. So for number 1, we're just going to look for the dimensions here. 2.83. Oh, you know what I didn't do was around this corner. Let me just see here. I didn't solve for this length. Let me just see if it's going to be easier to do this. We have that length, and we have that length, and then we have this length, 2.83, and we have that length. So that actually might be easier to divide it up that way. So instead, let's do this. Oh, I wish I had my white out. Okay, let's cancel that out. So we'll make this. So this whole thing here is going to be number 1. Okay, and then number 2 will be this guy. All right, so number 1 is going to be, we had this length was 2.83 repeating yards, and it's going to be multiplied by the length here, which was 6.8 repeating yards. So that's going to be 6.8 repeating. So that's going to give me 19.518 yards. And it's going to be squared because we're finding area. Okay, for rectangle number 2, we're going to be looking at, let me just confirm I did that right, 6.8 times 2.83, yep. And then for rectangle number 2, we had the height was 2 and the width was 4, so 2 yards times by 4 yards, a little bit easier, gives us 8 yards. So then we want to find total area, which is just adding those together. 19.518 plus 8 equals plus 8, 27.518. Yards squared. Now, so that's the total area she has to cover. Now, remember that in the question they did say that she has to order about 10% extra. So if we want to find out the total amount that she has to buy, if this is her total area, we need to add 10% to that. So first, let's find 10%. So times by 10 over 100, or 0.1, which is going to give us 2.75. 1, whatever. And so then for the total plus 10%, we're going to have 27.518 plus 2.75, 51, whatever that decimal was, gives us 30.27 yards squared as her total that she should buy, including the extra that she wanted. Okay, then the next question, so we have the total that she needs to buy. The next one is where should she buy it? So with this, we just need to compare our costs. So for part B, if this is her amount in yards, she has 30.27 yards squared. We just need to multiply that by the price, right? So if she had, it said locally, it was 36.95 for every square yard per yard. So 30.27 times by 36.95 gives us a total cost of 1,118.49. So of course with money values we always round to 2 decimals. The other option was 30.27 yards squared times by, the other cost was $33.99 per square yard, which gives us a total cost of $1028.89. So it looks cheaper than this one, but remember there's a $100 delivery charge, so we need to add $100. And that gives us $1128.89 as her total cost. So when asked where would she buy, in a written question, hopefully you can write out a good enough answer. So what I would probably say is I think she should buy locally because it saves her, like, not a lot of money, it's $10, but also consider the fact that she doesn't have to have it delivered, which means that people aren't driving around, which is good for the environment. So, and also you're supporting a local business. So those are some good reasons for her to choose the local option. All right. Okay, so that was question number 4. I'm just trying to remember what was the next one. Question 7. Okay, so with question 7, we are asked, we have an airplane starting at point A. It flies north 30 degrees east at a speed of 125 miles per hour for 5 hours to point B. Then it flies south 20 degrees east at a speed of 100 miles per hour for 3 hours to point C. And the first thing is to make a scale drawing of the airplane's flight path. So the first thing that I would do in a question like this is, because you're given angles with the direction, I would start out by trying to represent that. So the plane starts somewhere, right? So let's say, hopefully this is relatively straight. So let's say this is going to be the starting point for the plane. Starting point for the plane. I'm going to draw a circle in the middle here. So they go north, so that's going to be at 90 degrees, but 30 degrees off to the east. So east is always on the right hand side here. And so we want to go 1, 2, 3, 30 degrees. So basically at 60 towards the east. That's the direction they're flying in. Okay. And then personally what I would do is I would draw like a little dot here just so I can keep in mind where my direction lines were, so that I know that this is like straight east from where I started. And the plane is flying in this direction. But what I want to do, because I'm making a scale drawing, is it's great that I have the direction, but I also want to kind of think of what I could do as a scale to represent that first distance. So in the beginning it says they travel at 125 miles per hour for 5 hours. And because we're trying to draw a scale drawing of the plane's flight path, we don't really care too much about the speed, but we need to know how far did they travel. So remember, with speed and time, you can always say, okay, if I did 125 miles per hour, how many hours did I travel for? 5. So I just multiply those two values together, and that gives me my total distance. So that should be 625 miles. Is from point, let's see, what did they call it, point A to point B. Okay. So if I want to draw a scale drawing, I want to think, how can I represent 625 miles? easy way for me that I can see right away what are the numbers I have on my ruler. Well, I have up to 6, 7, I have like somewhere in that range. So what if I just made each, like divide this by what, 100, and then made that equal to centimeters. So essentially for every 625 miles, I would have 6.25 centimeters, right? So 625 divided by 100. So that's my scale factor is 100 equals 6.25 centimeters. So now when I draw, I want to draw my line going up to 6.125, right about there. And of course, this is never going to be super accurate. So this is my actual end point. Okay, then the next component was where he flies from B to C. So maybe let's first solve for the distance for this one. So from B to C, it says he goes 100 miles per hour. And he travels that speed for 3 hours. So if he's going 100 miles each hour and he does 3 hours, that's 300 miles. So 300 divided by 100, use the same scale factor, of course, gives us 3 centimeters. Okay, so we need to look for direction. Now remember when you're doing these, basically what you're always going to be looking at is you have to keep your directions set up properly. So this is going to be kind of like our baseline now. So if he's at this point, we want to keep our protractor kind of like on a straight angle here. So it says that they go south. So that would be 90, right? Because this should be pointing straight down again. But it says 20 degrees east. So we have to go 10, 20 degrees in this direction. So I'm going to make a little mark at 70 right here. Okay, and that's the general direction he wants to go from here. Now all I need to do is make sure that I put in the correct distance that we found, which was 3 centimeters. So if I start here with 15, let's say, I'm going to make sure that I put my ruler to the point where I'm going, right? So it's in the right direction. And now I can just find my distance by going 15, 14. So that's 1 centimeter, 2 centimeters, 3 centimeters. So I'm going to stop at the 12 mark there. And that's going to be my point. So I had A, B, C. Okay, so that was asking us to make a scale drawing for the airplane's flight path. So you would maybe just want to write in here 6.25 cm equals 625 miles. And 3 centimeters equals 300 miles. So there's our scale drawing, but the last thing that it asks us is explain how you could estimate the distance from point C to point A. So if we wanted to estimate this distance, because this is drawn to scale with the correct angles and everything like that, what we could do is, now in a written question, you would maybe just explain this, although it's always good to back it up with a number value. So you should be able to just set your ruler down and say from point A to point C, the distance is 5 centimeters. So A to C, 5 centimeters. And given our scale factor, we would, because we divided by 100 to solve for this, we would multiply by 100. Is we can estimate that it would be about 500 miles. Okay, so basically on a written question, you would just explain, because this is drawn to scale, I can measure the distance between A and C and then use my scale factor to determine the distance in real life. And that will give me an approximate, like a good estimation of the distance between A and C. It's not going to be 100%, but should be pretty good. Okay, so that was number 7. The next one we're going to look at is number 8, which is looking at pizza. And it is almost lunchtime right now, so this is going to make me hungry. Okay, so the owners of a local pizzeria advertise their ginormous pizza as being 40% bigger than their competitor's pizza. They do not say, however, what they mean by bigger. If they mean that the diameter is 40% greater, what would be the percent increase in area? Okay, so let's start looking at that. Okay, so I'll just put in my number here. So number 8. So basically with A, we're thinking about if you have the diameter is 40% bigger. So what we want to think about with, it says if the diameter is 40% greater, what is the percent increase in area? So remember with a circle, it's not given to you directly on here, but if you had this kind of a question in a test, I would give you that formula. But basically the formula for the area of a circle is pi r squared, like we saw in that question about the cone. So area is going to be equal to pi r squared. Okay, and so they're saying if they mean the diameter is 40% greater. Now, if the diameter is 40% greater, then the radius is as well. So if we think about, let's do the competitor is going to be the original size, and the ginormous pizza is going to be the scale size. So with the competitor, they just have the original area equals pi r squared. Okay, now with the ginormous one, what they're saying is in part A is what if the diameter was 40% bigger, which would also mean that the radius is 40% bigger. The trick that you need to think about here is when something is 40% bigger, that means it's the full value of the original plus 40%. And so basically that means it's going to be 140% of the original. So essentially the area of the ginormous pizza is going to be equal to pi times by 140% of the radius. So essentially it's going to be like 140 out of 100 times by the radius squared. Okay. Now, because you're multiplying this value by the radius, and the radius is being squared, this value also has to be squared. So to simplify it, I would do 140 divided by 100 is 1.4. And because it's being multiplied by this thing that's being squared, we could write it out like this. Area is going to be pi times by 1.4 squared times by radius squared. And the reason why I like to write it out like that is because then that helps me to see that if I actually multiply that value, pi 1.4, when we square it gives us 1.96, and then we have radius squared here. So essentially when I have a formula like this where everything is just being multiplied through, if this side is now area times by pi times by radius squared was the original like the competitor's pizza, we have the same formula here, but on this side it's being multiplied by 1.96. If you multiply this side by 1.96, then that means the other side is also being multiplied by 1.96, which means the area is 1.96 times greater than the original, than the competitors. Okay, so if this side is being multiplied by that, so is the area. Now, what does 1.96 mean in terms of a percent? Because they asked what's the percent increase in area. So remember that the 1 represents that they have the full size of the competitor's pizza, 100% of their size, plus whatever is after the decimal is the increase above that size. So 0.96, if we think about what we did here, right, 140 divided by 100 was 1.4. So what we're ending up here is 196% of competitors size. And so what does that actually mean? If it's 196%, what's the percent increase? Well, 100% is where it's exactly the same. So the actual increase was 96% larger than the competitor. Okay. The second question asks us, if they mean that the area is 40% greater, what is the percent increase in diameter? Okay, so now we're thinking kind of the reverse way. So if we had area equals pi r squared here, again, we can kind of think the same way, pi r squared. And if the diameter is 40% greater, or wait, hold on a second. Sorry, if the area is 40% greater now. So now what we're saying is this area is 1.4 times as great, right? 140%. So 1.4 times by area is equal to pi times by radius squared. And what we want to solve for is how is this value going to affect the radius squared. So basically, figuring out how it affects the radius squared, what we kind of need to be aware of is what we said here, right? Which is that if this side is multiplied by 1.4 is attached to the radius, then it's a squared value, right? So that squared value is what multiplies across to the other side. So then the reverse is also true. If this squared value would be multiplied by the radius going that way, then if we want to figure out the actual change to the radius, we need to square root that value. Okay, so just think of it exactly like the reverse of this. So if we have, in this first part, we had a 1.4% or 1.4 times increase of the radius. So remember, we needed to square that value because it's attached to the radius squared in order to figure out how much of an increase that would be overall when applied to the other side as well. So now, essentially what this is like the squared value. And to solve for this, we need to square root it because the radius is squared over here. So we need square root of 1.4 is going to be equal to square root of, sorry guys, my microphone cut out there. So is equal to radius squared. So now if we square root 1.4, we should end up with 1.18. Area is equal to pi times by 1.18 radius. And so essentially what they were asking us is how much bigger would the diameter be? Remember what we set up here too, that the change in diameter, like if we think about it as a scale, is going to be the same as the change in radius. So what we're seeing here is that we have 1.18. So remember that that basically means 118% increase in the radius, which would apply to the diameter as well. So 100% of that is making it the same as the original, and then above that is the 18%. So what we see is an 18% increase in diameter or radius. It's the same because it's a scale factor. Okay. And then the last question says, which of these two meanings do you think was implied by the owners of the pizzeria? So that's a little bit of a more abstract question, but basically, I don't know, it's kind of up to you to say. I was even thinking like they could have meant that it's like 40% more mass as well, right? It doesn't have to be diameter or area. So you never know what they're talking about there. And that's the trick of marketing. Okay, let's see. Next question that we had was number 11, I believe. I'm just looking for my list. Oh yeah. Okay, number 11. So I'm just going to find myself a clean piece of paper here. So number 11, it says, I'll get rid of that. In a local store, Serena saw a toy pig with a scale ratio of 1 to 16. She estimated that the toy pig was about 10 centimeters long. She searched online and found a similar toy pig with a scale ratio of 1 to 64. And we want to estimate the length of the online toy. So basically what we're thinking here is we have a scale ratio of 1 to 16. Okay, so what that always means is that you have your original here, and is going to be 16 times bigger. So if we think about, I'm assuming, I mean, I find this actually kind of a poorly written question because it's a toy pig with a scale ratio of 1 to 16. What is the scale to? I'm assuming that means that it's ratioed to a real pig, which obviously would be bigger. So then the original is going to be the larger one, and then the toy is going to be the smaller one, which they said was 10 centimeters. So toy. And so if that's 10 centimeters is the length, then let's see, we want to figure out, because then she searched online and found a scale ratio of 1 to 64. So what I would recommend doing here is finding out what is the original length, and then you can apply that to the 1 to 64 scale. So if the toy was 10 centimeters, what would the original have been? Well, to go from 1 to 16, you would have to multiply by 16. And so same thing here. So if we have 10 centimeters was the toy, the original is going to be 16 times as big. And that's going to give us 160 centimeters is the original pig. Okay, so now if we want to solve for the other online toy, or the online toy, I guess, was 1 to 64. So essentially what that means is the original, like the real pig, is 64 times bigger than this online toy. So clearly this online toy should be smaller than the one that she saw in the store. So what we can say now is if this was the original length was 160 centimeters, we can solve for the scale length by going in reverse. So if this one was 160 centimeters, how do we get from 64 down to 1? Well, we would have to go 64 divided by 64, which would give us 1, right? So that means in order to get from our original height to the, or sorry, length, I guess, to the length of the toy, we need to divide by 64 as well. So 160 divided by 64 gives us 2.5 centimeters as the length. And then just really quickly, of course, you always want to think if that makes sense. So like we said, with the original pig and the toy that she saw in the store, it was only 16 times as big. But because this toy is much smaller compared to the original, because the original is 64 times as large, it makes sense that the length of the toy pig that she found online should be smaller than the original one, which was 10. So now we have a length of 2.5 centimeters. Yeah, so that's everything for number 11. The next question was question number 13. So Jonas collects and builds model airplanes. He wants to build a 1 to 20 scale model for a float plane, and he finds the dimensions of the plane, and then to make this more complicated, he wants to build a glass display case for his model that should be 20 bigger than each dimension of the model. Okay, so what do we all need to do here? Well, first of all, we need to think we have the dimensions of a real plane. What are going to be the dimensions of his model? Then once we know the dimensions of his model, we can figure out what 20% of those sizes are, add them to the sizes that we calculated, and then that will help us to solve for the size of the case. So basically what we would need to do is, let's see, this is question number 13. Now I'm going to astonish you guys with my drawing skills again. So we've got plane and I don't know, something like that. So what are the original dimensions? Well, it has a height of 7 feet and 6 inches. They really like to give us those feet and inches measurements. It has a length of 26 feet and 2 inches. And then it has a wingspan, so I'm going to kind of draw another little one over here, of 36 feet. So that's representing the wingspan. So first things that we want to do, I would first of all convert everything into inches, especially because you're going down into a smaller scale model, so you'll probably want to measure that in inches anyways. So let's do wingspan. This was the length and the height. Let's get those values. Okay, so wingspan is 36 feet, and if we use our data table, we know that there's 12 inches in a foot. So 36 feet times by 12 inches. Remember the units you want always on top per foot. So 36 times by 12 gives us 432 inches. Okay, and then for the length, they have 7 feet. So again, times by 12 inches per foot gives us 84 inches. And we need to add the additional 6. So plus 6 gives us 90 inches. All right, and then the height was 7 feet 6. Oh, shoot, I think I mixed those two up. Yeah. Okay, let's rotate those around. Okay, so length is 26 feet times by 12 inches per foot, which gives us 312 inches. And then we just want to add on the extra 2. That gives us 314 inches. Okay, so now we have all of our inches. The next thing we want to do is solve for this scale. So it said in this scale, it's 1 to 20. So that means if the original, there's 20 units in the original for every 1 in the model. Let's see. So basically what I would do is I would just figure out my scale is 1 divided by 20. Or no, wait, how did I do that? 20 divided by... let's see, could I do that? Times by 0.2. Let me just have a quick look here because... Oh, that's what I was doing there. Okay, never mind. Sorry, I forgot about that. So yeah, we can just divide all of these by 20, or you could multiply by 0.5. 0.05 shouldn't matter. So again, we're going to go wingspan. I'm going to switch these up so they're proper height and length. Okay, so we just want to basically divide by 20. 432 inches divided by 20 gives us 90 inches divided by 20 and 314 inches divided by 20. Okay, so when we calculate those, we end up with 21.6 inches for his model. Let's see, 90 divided by 20 gives us 4.5 inches. And 314 divided by 20 gives us 15.7 inches. Okay, so now we know the size of his scale model. And then the next thing we need to do is determine the dimensions of the case. So remember, for the case, he wanted each dimension to be 20% larger than the original. That's where I got my numbers mixed up earlier, is because I had multiplied by 0.2 and I was thinking for this part, but it's going to be divide by 20 or multiply by 0.05. And then now to solve for what is 20% of this, we can multiply by 0.2 or 2 over 100, or 20 over 100, which gives us 4.32 inches. And then same thing for all of these. That gives us 5.4, gives us 0.9. It's a bad time to run out of whiteout. Okay, 0.9 and then 3.14 times by 0.2 gives us 3.14. Okay, so now I know that 20% of these values are these. So to find the total dimensions of the case, you have to have the dimension of the plane, like the model, plus that extra 20% of space. So basically 21.6 plus 4.32, which gives us 25.92 inches. 4.5 plus 0.9 gives us 5.4 inches. And then 15.7 times by 0.2 gives us 3.14, and then plus 15 plus 3.14 gives us 18.84 inches. So then those are our dimensions in inches. I believe in the textbook they convert them back into feet. So just remember, if you want to convert into feet, you would just have to say 25.92. And remember, there's 12 inches in a foot. So if you just kind of think about it logically, we know that there are 2 times 12 would give us 24. 2 times 12 gives us 24. And that's going to fit into here. So that means we're going to have 2 feet plus whatever is left over. So 1.9 inches or 2 inches. Okay, this one, there is no conversion. It's just going to be 5.4 inches. And then this one, again, 12 goes into 18 one time. So we're going to have 1 foot. And that would equal 12. So the leftover to make it up to 18.84 would be 6.84. So we can just say plus 7 inches to round it off. And those are going to be our dimensions for the case. Okay. Let's try number 14. Just 2 more to go here really quickly. So with number 14, we have cone A is a reduction of cone B with a scale factor of 1 to 9. Cone A has a volume of 20 centimeters cubed. What is the volume of cone B? So with this one, what you guys might want to do is look at 8.6. I just want to find this thing that was in here. These formulas are a good thing to have in your head because they can help you to solve these kinds of questions quite easily. So if we look at that, let me just have a look here. So cone A is a reduction of cone B. So cone A is going to be our small one. Cone B is going to be our bigger one. And it tells us that the volume of cone A is 20 centimeters cubed. And we want to know what the volume is of B. Okay, so if you use those formulas that I just kind of showed to you, shoot, I probably should have kept that up. When we're dealing with volume, the volume of the similar object, so that's going to be cone B, is equal to the scale factor cubed times by the volume of the original object. Okay, and so with this one, we were told that we had a scale factor of 1 to 9. So basically that means the scale factor for B is going to be 9 times greater than A, right? Because A is 1/9. So what we can say is the area of the original was 20. We want to solve for area of B is going to be equal to K cubed. So remember, B is going to be 9 times as large, so 9 cubed. If B was smaller, you would want to use the fraction. So if it had been the other way around, if this one had been 20 and A had been 1/9 of this size, then you would want to do 1 over 9 cubed here. Okay, but because we're going to the larger one, we have to do the 9 cubed. So 9 cubed times by the area of the original, which was 20 centimeters cubed. And so 9 cubed times by 20 centimeters cubed gives us 14,580 centimeters cubed. Just keep in mind the centimeters cubed here does not mean that you cube the 20, it's just the units, okay? So that's our new volume. Okay, number 15, this is our last question. A chocolate bar is being sold in a package as shown. The manufacturer doubles the volume of the chocolate to create a larger bar, similar in shape to the original bar. So similar in shape always means that you're going to be able to use a scale factor for this. Okay, and that all the sides should change by the same amount, essentially. Determine the surface area to the nearest square centimeter of the package that is needed for the new bar. Now this is a little bit tricky because a lot of students would want to say, oh, okay, well I double the volume, so then I'm just doubling these dimensions to get the surface area. But keep in mind that that's not really how things relate. So first of all, what you need to figure out is what is going to be the new volume. Okay, so let me just see here. The manufacturer doubles the volume. Okay, so we need to know what the new volume is going to be. So the original volume is, now this one's a little bit tricky because it's this shape that we don't actually have on our, on our data sheet. So if that was a question on a test, I would give that to you. So you need to refer back to page 495 here where they have a bunch of different shapes. So we're looking at a right rectangular prism. We want to solve for the volume, which is 1/2 times base times height times length. So base times by height times by length. So if we look at this picture that they gave us, we have the base, we have the length, we do not have the height. However, you are shown that this base is 4 centimeters. If the height goes perfectly in the middle, right, because those red marks mean that each side is equal, so we know that this base is divided perfectly in half to make this triangle. And so we can actually solve for the height here. So essentially what we have is, if this is our height, our base was 2 centimeters, and they gave us this length was 4 centimeters. So if we want to solve for height, what are we going to do? Well, this is a right triangle, so we can use Pythagoras. Just be careful because we know the hypotenuse. So remember, Pythagoras is c squared equals a squared plus b squared. But because we have c squared, we need to rearrange the formula to solve for, it doesn't really matter if you call this a or b. Let's call it, let's call this one a. So we're going to basically do a squared equals c squared, and then you've moved this b to the other side by subtracting it. So now we can say, okay, height, which is what we called a, is going to be equal to the square root of c squared. So 4 squared is 16 minus b squared, which was 2 squared, which is 4. So square root of 16 minus 4, which is square root of 12, which is 3.46, some kind of a longer decimal centimeters. Okay, so now we have height, and so to solve for our volume according to the formula we just looked up on page 495, we have to do 1/2 times by base times by height times by length. So we have all of those values now, so we're going to do 1/2 times by, the base was this full base, so that was 4 centimeters. The height we just solved for is that 3.46, and the length was 20 centimeters. Okay, so if we multiply all those together, we end up with 138.56 centimeters cubed. So that was our original volume. Now it says in there that the manufacturer is going to double the volume. So what does that mean happens to this? New volume is going to be 2 times by 138.56 something, which is going to give us 277.128 centimeters cubed. That's our new volume that we want. Okay, so now if we want to solve for the new surface area, basically what we need to figure out is what was our scale factor to get from 138.56 to 277. So remember in the previous question we kind of talked about that, where you have the area of the changed object or similar object is equal to our scale factor cubed times by our original. So we have the volumes of both of these. Oh, sorry. Did I do area here? This should have been volume. There we go. Yeah. Okay, so yeah, with volume, because you just have to be careful, because if it was area, then the k value, the scale factor would be squared, not cubed. So just be careful with that. Okay, so we have new volume. So basically what we can say is our new volume, 277.128 something, is going to be equal to k, which we don't know our scale factor yet, cubed, times by our original, which was 138.56. And so basically if we want to solve for our scale factor, we need to divide away the 138, which we also kind of just figured out it's doubled, right? So we know that 277 divided by 138 is going to be 2 is equal to k cubed. And then if we want to just solve for k, we need to cube root that side, which means we need to cube root that side. So now we know k is equal to the cube root of 2, which is 1.259 something. So there's our decimal. So now that we have our k value, all we need to do is solve for, because what we're ending up looking for is what is the new surface area of this bar. And so basically what we would need to do is figure out the original surface area, and then we can get our new surface area using our k value. So what would be the original surface area? So again, if you look on page 495, you will find that there's a formula here. Base times height plus length, a plus b plus c. So a, b, c, it's basically the dimensions of the triangle on the front. So let's go through and do that. So the original surface area was base times height. So the base was 4 times by the height was what we calculated here, the 3.46, plus we want length, which was 20, times by a plus b plus c. Now all sides of the triangle were 4, so basically 3 times 4. And when we do that, we end up with 253.8 something. So that was our original surface area, and we want to solve for the new surface area. We have our k factor, so our new surface area is going to be k squared. Remember, when your surface area, it's squared, so 1.259 squared times by our original surface area, 253.8 something, and that is going to give us 402.97 something. So again, we can round it and say that we have 403 centimeters squared as our new surface area. And just think real quick if that makes sense. We had 253 here. It's hard to make like an exact estimate, but you know, you doubled the volume and you're at about 400 centimeters squared. So kind of getting closer towards doubling the surface area as well. So that seems like an appropriate value. Okay, so that was super, super long, but hopefully that helps you with some of the more complicated questions for Chapter 8. And let me know if you need me to help you with any of the other questions in that review.